Dear students, today we will discuss interpolation by unevenly spaced points. So suppose we have this data which is unevenly spaced. That means the distance between x0 and x1 and x1 and x2 is not same. They are differ. These are total n plus 1 data points. So now since we are talking about the interpolation, so we are trying to fit a polynomial, suppose denoted by px, which satisfies the interpolating condition. That means pxi is equal to f of xi for all I equal to 0 to n, because here I starts from 0 to n. Fine. So to get this goal, we have two methods. One is Lagrange's interpolation method, another one is Newton's divided difference interpolation method. Today we will discuss Lagrange interpolation formula. So here Lagrange interpolation formula. So here suppose we have two data points only. For example, here n is 2, n is 1. If n is 1, then what we have? We will have x0 and x1. That means two data points only. Then we can fit up linear interpolation. If we are having three data points, initial three data points, then we can fit a quadratic interpolation. If we are having four interpolation data points, then we can fit a cubic interpolation. That's why if we are having these n plus 1 data points overall, then we can fit a nth degree polynomial. So this phenomena is shown here. So now we will start with linear interpolation, then we will develop quadratic interpolation, and then we will generalize the Lagrange interpolation formula. This is our strategy. So we have divided the proof into three parts. So let's see. First part. Here is the first part. Linear Lagrange interpolation formula. So if we have only two data points, which is x0 and x1, corresponding values are f of x0, f of x1. So since we have two data points, so we can fit a polynomial of degree 1. We can fit a polynomial of degree 1, suppose denoted by p1x. Here 1 represents the degree of the polynomial. So this is the polynomial. p1x is a0 plus a1x. Two unknowns are here. To find out their values, we are having two conditions, so we can easily find. So now here, this polynomial is an interpolating polynomial, and obviously this will satisfy the interpolating condition. So put x is equal to x0 here. So this f1x is nothing but f of x0. Here p1x0 is nothing but f of x0 according to the interpolating condition, but according to here p1x is nothing but a0 plus a1x. So a0 plus a1x0. Similarly, use the second condition here. So we get f of x1 is equal to p1x1, but according to here p1x1 is a0 plus a1x1. So this is equation number 3, this is equation number 2, and this is equation number 1. So now we will eliminate a0 and a1 from equation number 1, 2 and 3. So we get this system of equations, eliminate a0 and a1. So we get this determinant. We get this determinant. Here p1x, coefficient of a0 is 1, coefficient of a1 is x. In the second equation, left hand side is f of x0, coefficient of a0 is 1, coefficient of a1 is x0. Similarly here f of x1, coefficient of a0 is 1, coefficient of x1 is, a1 is x1. This is equals to 0. Simplify this. Now to simplify this, we have two options. Either we will follow row wise expansion or column wise expansion. If suppose we are using column wise means along first column, then we will get Lagrange interpolation formula. If we follow the row wise expansion, then we will have Newton's divided difference formula. Fine. So today we will discuss only Lagrange's interpolation formula. So now we will expand this determinant column wise. So here p1x multiply by this minor, which is 1x0, 1x1. Fine. So we have to eliminate this. So we get this, which is equal written here, minus f of x0, which is, now eliminate this. So we get 1x, 1x1 here. Then plus f of x1, this. So eliminate first column and last row. So we get 1x, 1x0 is equals to 0. Simplify this, so we get P1 from here x1 minus x0 minus f of x0, x1 minus x plus f of x1, which is x1 naught minus x is equal to 0. So from here P1x is, you can bring all these things in the right hand side and then divide by x1 minus x0. So we get this x minus x, no, 1 divided by x0 minus x1 multiply by this f of x0 plus x minus x0, this quantity, divided by this x1 minus x0 multiply by f of x1. Fine. Now represent this, which is again a polynomial, because x is a variable quantity, x1 is a constant, x0 is constant, x1 is constant. So this is a nothing but a linear polynomial denoted by L0 x. Similarly here this quantity is a linear polynomial in x, which is denoted by L1x. Here L0 and L1 both are known as fundamental polynomials, Lagrange's fundamental polynomial. So P1x is L0x plus f of x0 plus L1x into f of x1. So here L0x is this, a linear polynomial, L1x is this, and these are called as Lagrange's fundamental polynomials, which satisfy the following condition. Now here if you put x equal to x0, then what you will get? 1. If you put 0, if you put x equal to x0, so we get 1, but if you put x equal to x1, then you will get 0. On the other side here, if you put x equal to x0, then you will get 0. Put x equal to x1, so you will get 1. So that's why we can say that here when index is 0, x0 is 0, the value will be 1. Similarly here when here is 1, here is 1, the value is 1. If here is 0, here is 1, then value is 0. Similarly if here is 1, here is 0, then again value is 1. So this linear function actually behaves like Kronecker delta function, which is defined as this. So Lixj can be written as delta ij, which is 0 if I is not equal to j, or equal to 1 when I is equals to j. Now when you plot this function, these functions, then what is the behavior? Here put x0 is 0, put x0, x equal to x0, so we get 1. So this is 1 at one level. Similarly here put x equal to x1, so we get 0. So just join these two. So this is the line L0x. Similarly here put x equal to x0, so we get 0. Put x equal to x1, so we get 1. So this is the line of L1x. Fine. So now when you plot the overall function, because this data is in terms of f of x, and here you have evaluated px. Here you have evaluated p. So just draw the function. Here this is the true curve and this is the line p1x. We have only two data points. This is the actual pattern, however this is the approximated pattern. So this is the error. These are the 2 points, x0 f0, x1 f1. This is the exact curve, this is the approximated curve. So this is the error. To find out the error, you can take the difference, fx p1x. And obviously this difference depends upon x, because here the error is this, however here the error is this. So error depends upon x. X varies from x0 to x1. That's why error is a function of x. Error depends upon f and x. Fine. This is the error function. Now if suppose, this is the second part now, if suppose we have 3 data points, then obviously we can fit a polynomial of degree 2, which is denoted by p2x. So here is p2x, which is equal to a0 plus a1x plus a2x square, where a0, a1, a2 are arbitrary constant, which are to be, they satisfy the interpolating condition, and this is the interpolating condition. These are the interpolating condition. Now substitute the values. So here f of x0, but p2x0 is according to our assumption a0 plus a1x plus a2x square. p1x1 is p2x1, but this value is nothing but a0 plus a1x plus a2x square. Similarly f of x2 is equal to p2x2, but f of x2, this quantity is nothing but a0 plus a1x2 plus a2x square. So we have 2 equations. So now eliminate a naught, a1, a2 from equation number 1 and equation number 2. So we get this system. So eliminate from 1 and 2, we get this system, eliminate a naught, a1, a2. So what we get? We get this determinant is equal to 0. Again expand this along first column. So we get p2x. So we get this. This is the minor. Minus f of x naught. So eliminate second row and first column. So we get this minor. So this is written here. Similarly, positive, alternately positive, negative, positive, negative. So positive is here f of x1. So we get this minus last f of x naught, eliminate the last one. So we get this minor is equal to 0. Simplify all these. So ultimately after simplification, so simplification process is shown here. So after simplification, what we get? We get this polynomial. Here. Again, this is represented by L0x, this is denoted by L1x, and last term is denoted by L2x, where L0x is this quantity, L1 is this one, this polynomial, L2 is, again the behavior is like a Kronecker delta function. If x is x0 here, then you will see that its value is 1. If L0x is x1, then its value is 0 due to this factor. Again L0 x2, then again 0 due to this factor. So the behavior is like this. Here behavior is this. At x1 its value is 0, at x2 its value is 0. However at x0 its value is 1. So behavior is like this. Similarly L1x, put x equal to x0, so value is 0. Put x equal to x1, its value is, put x equal to x1, its value is 1. And when x equal to x2, again it's 0. So behavior is this. This is the behavior. Similarly here, put x equal to x0, its value is 0. Put x equal to x1, its value is 0. And put x equal to x2, its value is 1. So behavior is this. Fine. So again this behaves like a Kronecker delta function. In here, this is the 3 points x0, x1, x2. This is the actual curve. And red one is actually the approximated curve p2x. Fine. So this is the, again error depends upon the x. So that's why when you find out the distance, this magnitude, this is the error function. And now here is the general formula. Here is the general formula, and I will discuss this general formula and example in the next video.